Thank you. Good morning. So I will talk about a mean to perform identification of the parameters of an image-based model using integrated digital volume correlation. During my PhD thesis, I work on ceramics matrix composites for aircraft engine. So it's those kind of composites are 3D woven silicon carbide composites. That means that the matrix and the fiber are both in silicon carbide. And it can be as a scene of unbrittle ceramics. The big advantage of those materials is that they have a very high stiffness, quite the same as the one of silicon carbide, and a very stable mechanical property with respect to temperature. So they are good candidates to replace the superalloy just after the reactor in the turbo reactor. And the aim is to be able to increase the operating temperature of the aircraft engine from 1,300 degrees Celsius to 1,500 degrees Celsius. So increase the efficiency of the thermodynamical reaction inside of the engine, also reduce the fuel consumption of the airplane traffic. But those materials have a very complex mesostructure. And with the complex mesostructure, they also faces quite complex loading. So here is some simulation that have been done, but on a superalloy wood of some fixed blade in motor. So they are submitted to a quite complex temperature field that induce very complex mechanical loading. And so the objective is to understand if the influence of the mesostructure of CMC on the coupling with this complex thermomechanical loading. And in terms of structure, so here you can see it's a slice of tomography that has been taken at synchrotron. So I think the resolution is something like 3 micron per pixel. And in this image, you can see the complex mesostructure of the material. So the complex arrangement of the toe. Here it's a kind of elbow shape part. So you can see here that the toe are not straight. The density of toe is not homogeneous inside the part. And as the matrix is made by chemical vapor deposition, it's a quite complex manufacturing process. There is a lot of irregularities, such as porosity, and the matrix is really heterogeneous at the mesoscale. And to be able to take into account this heterogeneity at the mesoscale, we wanted to model it at this scale. One of the difficulty here is that we cannot build a complete image-based model. So we mixed data from simulation and data from images, because in fact the quality of the image it's difficult to segment the matrix from the toe. So we simulated the waving process to have to obtain a waving pattern inside of the sample. And so we use this simulated waving on some textile descriptor to build an image of the woven structure of your sample. And then we superimpose this 3D image of the waving to information from tomography. And this information from tomography is typically the shape of the matrix, so the external shape of the sample on the sub-voxel porosity. And then just by summing those two images, we can have an images where each color corresponds to a level which corresponds to a material phase. And which was I studied the behavior of the material only in thermoelasticity. So we make the assumption each phase is thermoelastic, that their properties vary linearly with temperature. In fact, those variations are very low on the range of temperature that has been in use. So a linear approximation is quite good. And we use for those property initial estimation for the literature. So the matrix, which is in dark blue in the image, we suppose it is homogeneous isotropic. For the tau, we consider the transverse isotropic. And then for the void, we consider a material with a very low Young modulus. Just for numerical reason, it's easier to do. So, but on this kind of model, if we want to describe explicitly the mesostructure, it's an induced model with a lot of degree of freedom, and we wanted to reduce those degree of freedom. So we use a local homogenization strategy that has been developed by Jean Benezech during his PhD thesis. And this strategy consists, in fact, in using a macro-scale mesh and affecting to all the elements of this macro-scale mesh properties that are issued from a local homogenization of the phase it contains. And this homogenization is quite simply performed using equivalent laminate model. So in fact, the stiffness matrix of each macro-scale element is a mean of the stiffness matrix of the material it contains. And then we can obtain fields of property that depend from the element. On those fields, we can continue to see the geometrical feature. So the fiber element are visible in the, for example, in the property. So here one is the x-axis, y is the y-axis, and 3 is the z-axis. So now we have a model which is a digital twin of your sample. And it provides a quite fine description of the behavior. So qualitatively, it provides dualistic data, and we are able to see the influence of changing the mesostructure in the behavior of the part. But one big question remains is how to confront those models to experiments and to do it in a quantitative way. So we developed an identification procedure. And inside the identification procedure, I include the development of the experiment, the way the instrumentation was made, and the identification process itself. The in situ experiment we made was, we call it a high temperature corner bending test, because the sample has a corner shape. So it was performed at about 500 degrees Celsius, but with a very huge thermal gradient of 200 degrees Celsius per centimeter, which is just applied thanks to this resistor here. So that created a thermal gradient in the horizontally in this direction. The mechanical loading is applied stepwise with this punch that just go down during the test. And the experiment is instrumented with full field measurement. So the first measurement technique is tomography. So here you can see the centimeter of Psyche beamline at Soleil. Here's a loading device. And we also put an infrared camera to be able to measure the external, the temperature field on the external surface of the sample. And we choose to design the loading device with rotating gantry. So you can see here the steel column you have here rotate during the tomographic acquisition, so that there is no windows between the infrared camera and the sample, and we are able to measure the temperature field. But it creates some problem on tomography then. So we have this test, and this test provides us so first the sinogram with some missing data due to steel column. So I have developed a little reconstruction algorithm to be able to take into account those missing data and to have a tomogram with few artifacts due to this. We also create thermography. And those thermography are reprojected inside the surfaces of the 3D finite element mesh using a kind of stereo vision calibration algorithm. And we also measure the force during the test. You have just here the load cell. And we want to use both those three measurement modality in an integrated digital volume correlation procedure. And now I will detail how this kind of procedure works. So here is just a general recall about identification. So if we consider that model is a kind of function to which if you give it a set of parameters, such as constitutive parameters, parameter links to boundary condition, initial condition, parameter also linked to the geometry of the sample, it will give you some physical fields, typically strain, stress, and temperature, etc. And the identification is the inverse problem, consisting in knowing the model on some measured physical field to find the best set of parameters that give us those information. And typically, for in situ tomographic experiment, what we do is from the volume, we have a first measurement procedure that provides us kinematic measurement. And then from those kinematic measurements, we can perform an identification using the model to find the model parameter. But in fact, this approach is not always most relevant, because there can have some hypotheses during the kinematic measurement. And so we prefer to use what we call integrated measurement process. So in fact, passing directly from the raw measurement data to the model parameter, to the parameters of the model. So, and in practice, how we do that? So the digital image or digital volume correlation are kinematic measurement techniques that are mathematically exactly equivalent. So I use illustration about digital image correlation. It consists in finding the displacement field that minimize a residual, and this residual is defined as a difference between an image of the sample at an unloaded state minus an image of the sample at a loaded state corrected by the current estimation of the displacement. And we usually do this minimization on the wake form of the residual. The particularity of global digital image correlation is that we express this displacement field on a finite element basis. So any finite element mesh that respects some consideration about the images or the speckled pattern as to be the size of the element are typically determined by the texture of the image. And expressing the displacement field on a finite element basis, we can rewrite the problem as you have here. To perform as it is nonlinear, we perform the minimization using a Gauss-Newton algorithm, which is just solving this equation at each iteration. And the difference between integrated DVC and classical global DVC is that we doesn't choose to express the displacement field on a finite element basis, but in fact in any relevant basis. And typically we want to use the basis of the parameters of our models. So we can write exactly the same problem, but replacing phi by a new shape function, which we call psi here. But most of the time, we don't know explicitly the shape function psi, because there is no the mathematical link between the parameters and the gray level of the image is not known directly. So what we do is that we can use a kind of mathematical trick, so we can express the Hessian matrix of the integrated DIC problem in function of the Hessian matrix of the global DIC problem, passing through sensitivity fields. So sensitivity fields are typically the displacement field induced by an incremental change of the parameter inside the model. So just the partial derivative that can easily be computed numerically, making the difference between two finite element simulation. In practice, how do we implement integrated DVC in the studied case? So we first suppose a weak coupling between thermic and mechanics. So we can just use measured temperature field as a boundary condition in your problem. And then we couple the force on displacement measurement in the minimization problem. So we construct a new Hessian matrix combining both displacement data and force data. And what we have to care about in this kind of problem is that they are ill-posed, and so we have to be numerically to be a little careful. So we used to normalize parameters so that variation of the normalized parameters will induce quite the displacement of quite the same order of magnitude at each time. So here is just example of normalization. Typically, all modulus are normalized by a nominal value. So typically the initial value we have for the modulus. And here for the thermal dilatation coefficient, we have some more exotic normalization, which is in fact just a way that variation of one of this well, a way to take into account the shape of the sample inside it also. And the other thing we have to care about is which way to put to which experimental data. And the good way to do it is to use the respective uncertainty on each measurement. So that is why data are ponderated by the variance of the noise of measured data. And here is the results of one of the tests we carried out. So you can see that the sample has it's well, the force displacement curve is quite difficult to exploit because there is some sliding, and it's not a conventional test. We perform 6 acquisitions during the test. So we consider during the first 5, the sample has an elastic behavior, and then it failed at before the acquisition F. So you have, for example, a little snapshot on the slide of tomography at initial state. Then the last, the same image at the last stage before failure. Typically, we don't see nothing in it in terms of damage, etc. as discrete. And then the failed image of the sample. And in these images, we can see that the design of the material worked quite well, because the main objective is to have very complex crack paths on this material so that it's not too brittle. You see there is a lot of different branches, etc., that follow more or less porosity bundles, etc. And so the results of the measurement was first the temperature field. So during the test, the temperature decreased a little because, in fact, during the first step, the punch was not in contact with the sample. The measured displacement field, so I put measured between quotes because, in fact, it's a simulated one with the identified parameter. And we can see that at the first step, we have only dilatation, and then we have a flexure of the sample on the x-axis. And the 2 results of the identification procedure are first the residual at convergence. So those figures are quite difficult to read, but in fact, they represent the remaining error after the identification process. So the first is the residual computed with the initial parameter, so your point of departure. And the second one is residual at convergence. And what we have to see, for example, is that the kind of lunula you have in red and blue correspond to the mismatch between the 2 images, and they reduce significantly during the identification process. But some error remain, but it's quite classical because the model is not able to describe perfectly the kinematic of the sample. And during the test, we identify sets of parameters, so 9 mesoscale constituent parameters at 2 temperatures. And I just put some example that we are able to identify some parameters with quite good uncertainty. For example, the Young modulus of the matrix, or what is more interesting, the transverse Young modulus of the tau, that are quite difficult to obtain by other means. But some other parameters are greater in certainty. That means that the influence in the given configuration is not so important. So it's not always a problem. It depends on how the experiment is representative of actual operating condition, etc. And to conclude quickly, while the enriched macroscale model we use provide a quite good description of the material behavior, we have been able to identify most of the material parameters and to provide a way to measure the remaining error after this identification. But there is a lot of work that can be done, still done, for example, working about investigation about damage, etc., or improving the model. Also, a lot of things to do. Thank you.
Thank you very much.